A device containing a pneumatic logic circuit made from 21 microfluidic valves could be used as a new type of air-powered computer that does not require any electronic components. The device could help make a wide range of important air-powered systems safer and less expensive, according to its developers at the University of California at Riverside. Electronic computers rely on transistors to control the flow of electricity, but in the new air-powered computer, the researchers use tiny valves instead of transistors to control the flow of air rather than electricity. Combining multiple microfluidic valves enables the creation of complex air-powered logic circuits. In the new study, Grover and colleagues made a device that uses 21 microfluidic valves to perform a parity bit calculation, an important calculation employed by many electronic computers to detect errors and other problems. The novel air-powered computer detects differences in air pressure flowing through the valves to count the number of bits. If there is an error, it outputs an error signal by blowing a whistle. As a proof of concept, the researchers used their device to detect anomalies in an intermittent pneumatic compression (IPC) device, a leg sleeve that fills with air and regularly squeezes a patient's legs to increase blood flow, with the aim of preventing blood clots that could lead to strokes. Normally, these machines are monitored using electronic equipment. The variations between the two types of computers come down to one important physical difference between electricity and air. Electricity does not have viscosity, but air does. There are also lots of little design details that are of little consequence in electronic circuits but which become important in pneumatic circuits because of air's viscosity. This makes the job a bit harder but also means we can do things with pneumatic logic that are not possible, or are much harder to do, with electronic logic. In this work, the researchers focused on biomedical applications for their air-powered computer, but they say that this is just the tip of the iceberg for this technology. Air-powered systems are ubiquitous, from the brakes on a train to assembly line robots and medical ventilators. By using air-powered computers to operate and monitor these systems, we could make these important systems more affordable, more reliable, and safer. Material time, the aging of materials like amorphous materials resulting from glass transition, is determined after initial solidification by the relaxation of localized stresses and medium-scale reordering. This process, induced by the out-of-equilibrium state of the amorphous material, results in changes to the material's properties, such as a change from ductile to brittle state in metallic glasses. A recent paper in Nature Physics postulates that this material time is reversible, dependent on the stationarity of the stochastic processes involved in physical aging. An investigation by Till Boehmer and colleagues found that this process is reversible in 3 metallic glass materials, indicating that the material time is indeed reversible. This research validates theories regarding the aging of materials, which have been investigated in other areas, such as atomic dynamics and the nonlinear physical aging process of glasses. While these studies do not provide time travel powers, they provide a better understanding of how materials age over time, including biological systems like our bodies.
Thanks for watching, like and subscribe.